Hello, my name is Adam. I am a PhD candidate at the University of Sydney. Today I'll be presenting my paper titled A Human-Centered Framework for Sonic Mapping. Acoustics itself, as a study in architecture, does not engage the environment nor its landscape and texture as a fundamental principle of design. This is where the study of soundscapes may come in, a branch of sound perception in relation to our mind, which is a recently emerging appreciation of acoustic ecologies theorized by Murray Schafer back in 1977. The start of building acoustic representation begins with physical models produced in the early 1900s, beginning with Wallace Sabine's model, later evolving into light beam method models, and then in the late 1960s, the rise of computer models began to take place, for example with ray tracing models, and later sound auralization models to listen to the acoustics of a modeled room. This research, however, will take the lab out into the field and test aspects of the soundscape using the designer as the agent. This employs a recording task for sound scene listening, which relies on the ear as the tool. The types of sites surveyed in Sydney CBD are places intended for sonic refuge within the urban environment. Once the listener is in place, they would begin listening to the sounds they can hear, while simultaneously recording the sound scene and sound pressure levels with their devices for an entire 2 minutes. Throughout the duration of this time, the listener would list all of the sounds they can hear in natural, animal, human, and technological sound categories. The paper then looks at different methods for representing the data taken from the urban environment. The first method employs taxonomies, such as Figure 2, to compile all of the perceived sound parameters from a site. In the second method explored in this paper under graphs, the sound frequencies of recordings are monitored using spectrograms. This visualizes sound at bandwidths of 1000 Hz and highlights the energy of sounds at any point of time. The scene is blurred with background sounds at the low frequency range, yet there are many discrete sounds that appear across the entire frequency range throughout the duration of this recording. While these two methods are useful tools to represent compacted data, they both present a dilemma. Neither can speak of the site itself, whether sonically or spatially. Given the advanced capabilities both designers and computers have today in 3D modeling, this research is heavily invested in such methods. A major aspect of this involves sonification tools that allow the designer to listen to multiple sound signals imported directly into the spatial model. Also relevant is the modeling of the site's surroundings, their surfaces, and absorption coefficients. This is essentially a reconstruction of the sites visited and the designer's recorded experience there. Using sonification or an available auralization software allows the designer to revisit their site study within the 3D model. Here it's obvious that the fountain right in front of the listener's location is the most dominating and continuous sound. However, listening alone does not recreate the full sonic experience here. The previously recorded parameters are yet to be represented, so the model then implements a simple spherical representation of each sound. This is encoded with perceptual sound parameters, as well as physics-based parameters. These values are extracted from each individual sound wave using a Fourier transform and graphically represented as the sphere's dimness over time. These spatial visualizations assist in understanding complex two-dimensional data of the physical sound wave. While the sonification tool is helpful, the spatial visualization has the potential to better inform certain sound characteristics too difficult to understand in 2D graphs. The development of representation within 3D models can therefore continue to explore a combination of the sonification tool and the spatial visualization of individual sounds, further completing the audio-visual representation of the environment. For example, the designer will have access to an immersive tool complete with data to make real-time decisions. In this hypothetical example, spatial patterns are generated using computational design with sounds incorporated into the combined patterns themselves. Finally, the sonic analysis can be read alongside other forms of representation, such as descriptive or graphical visualizations of the sounds present. This will help to try and understand where sounds are coming from and how they are concentrated in the built environment. To a certain degree, this research will adopt and pursue existing methods of representing the soundscape. However, there is a need to provide the designer some parameters to control the spatial qualities that impact the sonic experience, ultimately by bringing the user firstly into the environment itself. Thank you for listening.